Good afternoon, everybody, and thanks for coming to today's AJS. Today's speaker is Dario Coscia, who is a PhD student here at SISSA MATLAB in collaboration with the University of Amsterdam. And the title of his talk is The Bayesian Potential for Uncertainty Quantification in Simulation-Based Chemistry. So without further ado, Dario, the floor is yours.
Thank you, Lorenzo. Hi, everyone, both the one in person in Trieste and the ones online. I'm sorry I cannot be in Trieste. This is the second time at one AJS and I'm not in Trieste, which is a shame since I do a PhD in Trieste. But anyway, so yes, today we'll talk about this project that I've been doing a few months ago in Amsterdam, and I tried to write a catchy title, The Bayesian Potential for Uncertainty Quantification in Simulation-Based Chemistry, because we will go to talk about potential energy a lot, and also because it's a potential in the sense that it will, as you can see, unlock some real nice feature that you can use for simulation-based chemistry. Before starting, I want to acknowledge Pim Dehan from CASPI and Max Welling, because they also, from CASPI University of Amsterdam, because they also contribute largely to the paper, so I also want to acknowledge them. So what I will explain today, we'll have molecules as the driving examples, but it's not just for molecules. So I will always try to come back and talk about the general picture. We will work with graph neural networks. But as an example, a leading example, we will talk about molecules. And this is because basically molecules are everywhere. Everything that is material is made of molecules, of course, except for the four fundamental forces. And if you split them into quarks, except for that, everything is made up of molecules. And nowadays, a lot of people are using deep learning in this field for different applications. For example, drug discovery, in order to produce drugs in a faster way, catalysis design. For example, ammonia, which is a molecule that is used everywhere in fertilization. It can only happen when the iron is used as a catalysis. And this basically speed up the process of ammonia synthesis, and is actually 3% worldwide energy is spent for ammonia synthesis, so it's something pretty important. So catalysis design is something important, but also photovoltaics, green energy, carbon capture. I mean, there are many applications where molecules are in. So people are very interested in this topic, but of course it comes with some challenging, and that's why deep learning comes in, and that's why today's talk is about this. So what are the main challenges? So I will wrap up some of them and try to explain it easily. So there are mainly two challenges when dealing with molecules. The first challenge is how to compute energies of molecules. So why is it important? First of all, because with energies you can do multiple stuff. You can run MD simulation, molecular dynamics simulation. You can study the behavior of the molecule. But in order to compute this type of energies, what you need to do is to solve this equation over here, the Schrödinger equation, where H is some Hamiltonian, which basically is a function of potential energy and kinetic energy. And then what you aim for is to find this E over here, which is basically the ground state energy. And you do it by solving this equation, where psi is a so-called is a function of the atomic positions. What's the hard thing here? So you can see that this function depends on many coordinates, x1, x2, basically one for each atomic position. So basically, if you want to solve this is going to scale exponentially with the number of coordinates. And you can imagine that the number of coordinates in a molecule is pretty large. So if you want to try to put this in a computer, so you need to discretize the domain. Of course, this scales exponentially with the number of atomic systems, so basically cannot fit in memory. So this is the first thing. We can always solve in small scales. Of course, you can do some tweaks. There are people that do density functional theory with scales cubically, but still very bad scaling. So solving this equation is hard, and you can do it, but only for small molecules. And the second problem is, if we want to design new molecules, we need to search in a very high and complex space. So just to give you an idea, the ChemBL17 picture here, so this small area, this are all the organic molecules that we know nowadays. And now this big area over here, these are all the organic molecules that basically are estimated to be in nature. So as you can see, there's a big gap, and this is only for organic molecule. Think about inorganic, think about crystals, whatever. These are not considered. So you can imagine that you're looking for one specific molecule in a space that is so enormous, and for looking for this molecule, you need to solve an equation which is itself hard to solve. Basically, it looks like an impossible problem. So that's why physicians have come up with a lot of approximation, but also that's why deep learning entered into place. Because the idea is that, okay, if we can't solve this equation fast in order to explore this big space, we need, if we can't solve this equation fast to explore this big space, we need to solve it efficiently with some other methods. So it cannot be a physics method, but it would be a deep learning method. So basically the whole idea is to build a surrogate that can enable us to solve this equation in a fast way. And here is an example. It's called UMA, which stands for Universal Models of Atoms. And basically, this is a model that came out recently from Meta. And what it does is basically solving, finding energy and forces of molecular structures. And this model, now we will go more in details how this model works, are basically graph neural networks. And that's how it connects with machine learning. So what I will explain today is mostly about graph neural network with the application of molecules. But of course, if you have other field of application, PDEs, for example, or others, what I will explain is not just for molecules, so you can translate directly to your field of application. So what they do in this paper is basically, as I said, solving the quantum mechanical equation in an efficient way, because graph scales linearly with the number of atomic elements. So not cubically, not exponentially, but linearly, which enables them to solve very fast this equation and then explore the space faster and faster. So how do they work? Here is the animation. Basically, it didn't start, but this is the animation of how you can use this model for metal organic framework. So how do they work? How does this model work? So first of all, you start with a molecule. This is a physical structure. This is the ammonia that we were talking about before. And the first thing that you do, the really first thing, is to encode it in a graph-based structure. Here, the edge basically represents the relative distances between atoms, and each node represents the atom type, an encoding of the atom type. But now that you have a graph, so you have a representation of your physical structure, you know how to process this guy, and you can process it with neural networks. So you can do L layers of message passing neural networks, so L layers of graph neural network. You process the graph, you obtain a representation of this processed graph, and then when you have this representation, you decode. And by decoding, what you do is predicting energy, which is global, so per graph, and forces, which is local, which is per atomic structure. So this is very easy. And as I said, it's also not just for molecules, because you can imagine that this graph can be anything else. It could be PDE, it could be a representation of a specific solution of a PDE, where the node represents the value and the edge is just the relative distance between the mesh nodes. So you obtain this representation by decoding, where you obtain energy and forces, then you need to train. And for training, you can do it in two ways. So the first way of training is physically, it makes physics sense, let's say, because basically you just predict the energy with your neural network, where theta are the parameters of the neural network, and you compare it with a ground truth energy. And then, of course, if you want to obtain forces, you're just going to take the negative gradient with respect to the atomic position of the energy. And this makes sense because the force is defined as the negative gradient of the energy. So some people train these models like this. What is the catch? The catch is that if you want to take this gradient over here, you need to do it in float 32 precision, or float 32, or even float 64, which basically means you're going to occupy a lot of memory, which basically means that you cannot store in the batch a lot of graph structures. So people are saying, okay, but if we need to train this model at scale, so we need to train for a lot of physical structure, we cannot do this. So another way of doing it is way more simple. You just train the neural network to predict both energy and forces. Of course, this is simpler and it doesn't respect physics in the sense that you don't ensure that the field that you're going to get is conservative, because you're not sure that the force will be the negative of the gradient of the energy. There are many works that show that actually when you train with a lot of data, you can resemble approximately the first order derivative of the energy. It's not true for more order derivatives that sometimes are needed. So what people have been doing is first training in the direct scenario using float 16 precision or B float 16, and then fine tune with the conservative part. But anyway, this is just to explain you, this is just to explain you that this is the way people usually train this type of stuff. Okay, so great. This is how machine learning force field work. Also, if there are any questions during the talk, I'm more than happy to answer them while I'm talking. So they're great. They can basically solve this big problem. We are done. Well, actually, no. And here I show you an animation why we are not done yet. Let's see, the animation doesn't go. Here we go. So this is the same model as before, the UMA model, this foundation model for materials. And as you can see, the molecule, when I try to do a molecular simulation with this model, breaks apart. And of course, this is something that, I mean, you don't have to be a physician to know that this is not something that you want. I mean, you don't want your molecules in your body to break apart, right? So sometimes deep learning models can fail. There are several reasons why they can fail. For example, limited or poor data quality, optimization issue. Maybe you have not reached the full minimum. Maybe it's just a local minimum. Or because you actually tested on some out-of-distribution data. So there are many reasons why deep learning models can fail. And that's why what I research on is uncertainty quantification. So basically, the idea of uncertainty quantification is to build models that we can trust even when they operate in outside training regime. So the real question is, can we spot when the model doesn't know? And that's what basically uncertainty quantification tries to answer. And we wanted to do it efficiently. Why do we want to do it efficiently? Because if we don't do it efficiently, well, then you can just use a normal solver and use a prediction from the normal solver. So the idea is that we want to build, first of all, surrogates to be fast, and then we want also uncertainty on those surrogates in order to understand when the surrogate does understand something or doesn't understand something. And in case it doesn't understand, then we can use an actual solver to improve the prediction. So of course, some people have been doing it with ensemble, but ensemble are inefficient. So what I will present today is trying to bridge this gap, so doing uncertainty quantification in neural networks efficiently. And there are some ingredients in order to do this recipe. And the first one is Bayesian learning. So I think many of you are familiar with this formula over here. This is the Bayes theorem and is used to update beliefs given some evidence and likelihood. So this omega over here, it will represent neural networks parameter for us. And this D over here will represent
sorry
some
to interrupt you. For some reason, the pointer of your mouse is not, I mean, we do not see it in the same place you see it. So, I mean, it's well understandable. Okay. Just to let you know that, I mean, be careful a little bit when you point at things because we don't really see the pointer in the same position.
What about this?
Are you pointing
I'm
at
pointing
omega?
to the posterior. Yeah.
Yeah, okay.
It works?
Okay. Yes, it does now. Now you're with the highlighter, right?
exactly.
Yeah, sure,
Okay.
thanks.
Okay, sorry for
Sorry
that.
to interrupt.
Yeah, don't worry. I changed the way I'm presenting. Okay. So what I was saying is that this guy over here is the posterior distribution. It basically tells us how the model parameters update given some observed data. And basically this formula is analytical. You just take a likelihood, so how you predict given some parameter, you impose a prior over the parameter, and you marginalize, so you basically integrate over the parameter to get the evidence. So this formula is analytical, super good. And once you have this formula, you can also decompose uncertainty, and so you can obtain the total uncertainty, which is basically some sort of epistemic plus aleatoric uncertainty. This part over here is the epistemic one, so basically it tells us how much variance there is in the posterior distribution, and this one is the aleatoric one, so the ones that depends only on the data, and it cannot be reduced. We will mostly care about this type of uncertainty today, so how much uncertain we have in different models, and we'll not care about this uncertainty today. So what is the catch? So the formula is analytical. What's the problem? Well, the problem is the fact that with neural networks, usually this variable over here, the parameters, live in something like millions or even billions nowadays. So you cannot integrate. You cannot compute this guy over here. And if you cannot compute this guy, well, you miss out a normalization factor, which is super important in probability. So we cannot do this. We cannot compute this analytical formula. So what people have been doing is, okay, since we are dealing with neural network and neural network like gradient-based method and optimization, let's formulate the problem of finding a posterior distribution in a gradient-based method, in an optimization problem. So the idea is, okay, I want to find this guy over here, the distribution, the posterior distribution, so how my parameters are going to be once they observe the data. Here depicted like this. And in order to find it, I will approximate with a family of parametrical distribution that I will call Q of phi, where phi are the parameters of this distribution, which are called variational posterior usually. And the idea is that now we want these two distributions to match as closely as possible. So we need some sort of distance, some sort of divergence actually. And this is the KL divergence between the variational posterior and the true posterior. Now you may ask, okay, but this doesn't solve the problem because we don't know this guy, but actually we can do some math around it, and we will see that it's just a constant term minus something that we all know, because we know this and we know this. So the idea is, since we want to minimize this guy, and since this guy is always greater than or equal than 0, and since this is a constant, we just need to maximize the elbow. So basically we turn the problem of integrating and finding the posterior into a problem of optimization. And this actually helps, and there's many works in Bayesian neural network that do this approach, for example, based by Backprop, by Blundell, or many others. So people usually do this. But this is still not efficient. We need something more. And that's why we have another ingredient in the recipe, which is this variational dropout. So I think many of you are familiar with dropout, which is basically zeroing out some neurons in the neural network. Variational dropout basically is very similar, but it doesn't fix the dropout probability, it learns it. And you can imagine that if you learn the dropout probability, and every time you are randomly zeroing out neurons, this is like implicitly putting a distribution over the weights. So this is what we will use. This is this variational dropout. Here I leave some reference if you want to see it. And another thing that we will use is the local reparametrization trick. So right now, I always talked about sampling weights, so sampling neural network parameters. But actually, this is not efficient because they live in a high-dimensional space, and because you need independent sample for each batch, which basically it's overkilling for training this guy. So instead of this, we will use the fact that if we put a normal distribution on the weights, then the activation will be normal, because because linear combination of normal random variables are still normal. So by doing this, we push the uncertainty from the weights to the uncertainty deactivation. And this is way more memory efficient because now you can use the batch as the independent sample. So you don't need to sample weights, but you just need to sample batches. And this is way more efficient than ensembling, specifically in training and in memory consumption. Okay, so these are basically is the recipe. And now we will put in all these ingredients together to make a BLIP. So this is the Bayesian Learned Interatomic Potential, is the work that we've been conducting with PM and Max. And as I said, we want to build a surrogate model for graph neural network that is calibrated. So basically means that it knows when it's wrong and it knows when it's good. It's architecture agnostic, which means that it can work with any graph neural network or any machine learning interatomic potential, including equivariant architectures, and I will talk briefly about it. And then we want minimal overhead. So we want a very fast inference for energy and forces. Eventually, we want the same inference time as a standard machine learning, a standard neural network. So how do we build this guy? Well, we put together all the ingredients that we saw so far. So here I just put a layer of graph neural network. So if you go from layer L to layer L+1, this is what happened inside. So you have your graph. Your graph has some edge features that we call it Aij, and has some node features that we call it Hi, so for node I and layer L. So what we do is to create for each couples of nodes an embedding. In this case, it's a very simple embedding. And we pass this through a message function. The message function is just a neural network, and we need to sample the weights of the neural network from a prior distribution that we will, in a while, I will tell you more in a while. Once we obtain the weights, we can compute a forward pass, obtain the messages. We aggregate the messages. This is standard message passing procedure, and then we update with the messages the state H to obtain a new state with an update function that again is a neural network, and again you need to sample the weights. So basically this is a standard message passing neural network, but the critical difference is that you sample weights. And how do you sample? You sample with this distribution over here, which is a dropout distribution. So this distribution over here is equivalent in doing dropout, but it's written in a mathematical sense. And of course, you need also a probabilistic model, which is very simple. As we said, we sample first the weights, and then given the weights and the state, we obtain the new state. So this is just a mathematical way to write what we just discussed. So we have a prior, and now, as I said, we need to build a posterior. We need to build a variational posterior in order to do variational inference. Okay. So how do we do this? So we decided to build this posterior in this way. It's kind of complex, so I will try to unpack it for the different parts that why we decided to do it like this. So the first thing that we need is a distribution, is a parametric family, and this Q is modeled as a normal distribution. This normal distribution has two characteristics. The first one is the fact that the mean is proportional to the variance. So the variance is the square of the mean. And we do this in order to not include extra parameters in the neural network. So basically, your Bayesian neural network will have approximately the same number of parameters as the normal neural network. And the second thing is this coefficient over here, alpha, or here, beta. What does it do? Basically, it regulates how much uncertainty you will get in your neural network, and these depend directly on the input structure. So the idea is that given the input structure, of course, you embed it in a graph, and then with another neural network, and here is the parameter phi, you obtain these alphas over here. These alphas get passed inside the main neural network layers and perturb the weights. So you can imagine a neural network and these neural network weights get perturbed, and the perturbation strength is the square root of alpha. So this is how you inject noise inside the neural network. And why it's useful? Because now these alpha are aware about the input structure. So they will increase when they don't know, and they will decrease and be more confident when they know. So this is the catch. This is how we model calibration inside this neural network. Okay, then once you do this, you just need to train. And this is the formula that you use for training. It seems super mega ultra complex, but it's, I swear, it's very easy. It's just composed by a reconstruction term. And this reconstruction term is what we saw before, basically energy and forces mean square error. And then there is this big regularization term that actually, once you do all the math, only depends on alpha and beta and is analytical. So you can always add this extra term in your training. So if you think about it, training this guy is quite very similar to training a standard machine learning force field. You just need to add this scattering pipeline, which is quite easy, especially with Torch and JAX, and you need to add this regularization term. But the rest is the same. You can use the same architecture, you can use the same graph neural network, you can even use the same equivariant neural network. So if you're not familiar with equivariants and equivariant neural networks, what they do is basically impose in the architecture the group constraint of the structure. And I give you an example. So suppose that you have a molecule. Of course, the molecule, if you, for example, predicting forces, you would like the forces to turn around the molecule for you, and you would not like to learn this. You would like that if the molecules rotate, the model already knows that the molecule is rotating, so it rotates the forces itself. So basically, you would want the model to have this inductive bias. And you can build neural networks that do this. So they basically reproduce this diagram. And what we show in the paper, and I mean, you can read more about it in there, is the fact that if you build your alpha coefficient, this one over here, in a way that they are invariant to the input structure, then all this update can be used in an equivariant neural network without breaking equivariance. So you will still have equivariance in distribution. And we prove this in the paper. So if you're curious, you can go and read it inside the paper or in the question and answer session. So this is it. Is as I said, it's pretty simple. The idea is that you want to inject this alpha and this beta to regulate uncertainty in the neural network. And I will show you some example that we applied and some experiment, and they're mainly going to be based on molecule experiment. But before that, if there are not any questions, I will proceed. So we'll just take some seat. Okay, so let's see some experiment. So the first thing that we wanted to test is the following. So sometimes we train the neural network on a specific data set, and then we test it on a completely different data set, what is so-called out-of-distribution data. So can we spot this? Can we spot when we are in out-of-distribution? And to do this, we basically perform this test where we train for different configuration of ammonia and testing for other configuration. Importantly, we train in low energy regime and we tested in very high energy regime. Same with forces. So the out of distribution here is the fact that we test in energy regimes that the network has never seen, and we want to see if it can actually understand this. So here we report some results on the mean absolute error for energy and forces. And of course, with a bunch of baselines. The most important baseline is this deep ensemble over here, which is kind of state of the art, especially in uncertainty quantification in graph neural in neural networks when you have a lot of parameters. I mean, if you don't have a lot of parameters, you can do different stuff. You can do Markov MCMC or HMC, but if you have a lot of parameters, you cannot do it. So you need some sort of trick, and deep ensemble is one of these tricks, where basically they train multiple neural networks to predict the same stuff, and then they compute a variance between these neural networks. And as you can see, we do even perform better than deep ensemble in energy and forces. But the most important thing, the one that I wanted to show you, is this, is the calibration plot. So here I plot the predicted force variance per structure, so how much variance that we obtain for each structure, and the square error per structure. So what's the real error square that we're going to commit? And as you can see, we have a very good correlation. This basically means that we can identify up to this correlation when a molecule, when the model makes an error, especially even in out of distribution. So we can say for this specific molecule, given the predicted variance, I will get this specific error, which is quite something very, very nice. I mean, usually you cannot quantify in out of distribution regimes. And if you want also, let's say, a metric on how much calibrated you are, basically, probabilistically, the network knows when it's wrong, and with which confidence you can see the expected calibration error. And here as well, we do better than deep ensemble and all the other baselines. So this was the first test. So in the first test, we were very interested in testing small data set in out of distribution. In the second test, we were thinking something differently. We said, okay, now we're going to take a real material. And in this case, we took this silica glass. And we're going to take a pre-trained model. In this case, we took this Orb V3, which is a competitor of UMA. And we're going to fine-tune this model on this task for different training data sizes. And we're going to see if actually adding this Bayesian flavor can improve performances that can actually perform uncertainty quantification. So the first thing that you can do is, of course, fine-tune without BLIP, so standard fine-tuning. You fine-tune the model, and of course, as increasing data sizes, error decreases. Okay, that's something that you can always do. The line over here is the pre-trained model. Then what you can do is also fine-tuning with ensemble. And as you can see, this doesn't change a lot. And this is because you started from pre-trained weights. So you already are in a very good minimum. So if you start from the same minimum, and it's already a good minimum, you will not get a lot of variance during the optimization process. And so that's why ensemble don't perform that well. And then you say, okay, let's apply now BLIP. And you can see now there's a big gap in what we can obtain. Of course, as you increase data, they basically all perform similar. There's a bit of improvement, but not that much actually. But in low data regime, and that's important, the Bayesian regularization that you add during training can actually boost performance. So that's something that we found very, very nice. So it can work in small data regime, it can work in big data regime with pre-trained model. And then the last question that we asked ourselves was, okay, how can we use this uncertainty? So of course we can spot when the model is wrong, but are there other useful ways in which we can use uncertainty? And that's where active learning comes in. So basically the idea is, if we don't have a big data set, but I still want to train a machine learning force field, how can I find the most important structures for training? So the ones that basically will let convergence faster in my machine learning force field. And uncertainty for that are basically super useful. Because what you can do is start with a small data set, of course, train the model, so compute energy and forces. And then once you have these forces from the trained model, run an MD simulation with these forces and get to a point where this break or where the uncertainty are very big. And now, once you're in that point, pick that structure. You do this multiple times, and then for each of them, you compute the uncertainty, and then you select the one with higher uncertainty. So basically, you're exploring the space in which the model is most uncertain and selecting those structure. And then what you do is, once I select the structure, then I'm going to use an actual solver, an actual quantum mechanical solver, obtain the reference energy and forces, and train again. And you start again the loop again and again. And here I'll show you the result. So of course you can do this without BLIP, and at each step you just sample randomly. So you just perform MD simulation and sample randomly. And then, of course, you will get better results as you sample, because you increase the data set size, so validation loss will increase. But then you say, okay, I want to do the same, but with BLIP, without uncertainty. So we know that we will do better. As you can see, we do better. But again, we're not using uncertainty. So we are not selecting the most uncertain part of the structures. So what happens if we do select the most uncertain part is this loss over here. So of course, at the beginning, it's all the same because they train on all the same data set. Here, the selection comes. And as you can see, in the first step, you already have a big change in validation loss. And usually this is a very big change in this type of, for this type of application. Of course, as you increase data size, the change decreases. But the important thing here that I want to highlight is the fact that you can use actively this uncertainty to select data to train better your model. So it's not just saying when the model is wrong. It's more like, of course, we can use this, but we can also use it to improve the model itself while training. And this is something that I find pretty nice. So this is comes almost to an end of the talk. Why I said almost? Because as I said, this cannot be used. This can be used for molecules, but it can be used in general for any graph neural network. So this is a work that we recently got published in this workshop in Clear with Giovanni and Filippo, Nicola, and Gianluigi. And here we use graph neural networks, specifically GCROM, to perform reduced order modeling and add uncertainty on this. So it's the same approach, because at the end of the day, it's a graph neural network. But we add uncertainty in this graph neural network, where the uncertainty depends on the specific parameter of the reduced order model. And as you can see, we obtain a very good uncertainty that correlates pretty well with the error that we're committing. And of course, this can be used in an active learning loop, etc., etc. So if you're interested, of course, this is the paper. So with this, I conclude. I hope I kind of gave an intuition why uncertainty quantification nowadays it's quite important, AI for science, specifically for surrogate models. Then I try to present this approach that we developed, which is called BLIP. It kind of achieved good performance, state of the art in some experiments. But the important thing is that we can basically build any graph neural network and inject uncertainty in this graph and use those uncertainty for uncertainty quantification or active learning. Of course, I mean, the field of uncertainty quantification and scientific machine learning, I think it's growing and growing. We really need models, machine learning models that have uncertainty incorporated in those models. And we need smart uncertainty and efficient uncertainty. If we want to use big models, we cannot do standard uncertainty quantification techniques. So we need other ways to do it. And we try to give just a first hint with BLIP. So with this, I conclude, and thank you for the attention. If there are any questions, I will be very happy to answer them. Thank you.
So thanks a lot, Dario, for the very nice talk. So I would ask people in the room or also online if there is any question. If not, I have a couple of curiosities. Yeah. So they are quite, I mean, technical ones. It's just really out of curiosity. But first of all, I have a little bit of familiarity with graph neural PD solvers. And one thing that is interesting in that case is that the choice of for instance, the edge features that you pass to your models can, can affect performance. So I just wanted to ask whether you have like some sort of experience about the embedding from a molecule to graph, how to do that, and what kind of effect does it have on the performance of the network, also in the UQ setting, possibly. And then the second one was just if you actually try to perform fine-tuning using also the strategy with the actual gradient computation of the network when you mentioned, which you mentioned at the beginning of the presentation to ensure physical consistency.
Okay, so let's go a bit back. So I have a picture that we can use. I think it was this one. Okay. So regarding the first question, the bedding, I think those are kind of the most important thing when you train a neural network. Like how you build embeddings is basically going to determine your performance at the end. With physical structure, there are many ways in which you can build the embedding. So the naive way is for each atom, you do a one-hot encoding. Of course, that's a naive way. It kind of performs well, but you can do even more, right? You can even have a learnable embedding. You can, and sometimes what people do is also have physical embedding. So adding on top of, let's say, a learnable one, adding some physics. For example, you could add, some people use spherical harmonics as embeddings to ensure some equivariance. Like there are many embeddings that you can use. What actually I found very interesting, let's say, a representation of the molecule. And here, this network is pretty important because if it's too weak, this alpha will not understand the role of uncertainty. So what I found interesting is that for this paper, we use the same type of embedding as the main network. But for other papers that I'm currently doing is using pre-trained models as backbones to obtain embeddings, then pass these to this network. And this improves a lot over uncertainty quantification, of course, because he has a richer representation of the input. So I hope this answered the question. And regarding the second question, fine tuning. So here the fine tuning that we did was direct fine tuning. We didn't do conservative fine tuning because it's let's say it's easier and it's faster because computing gradients usually doesn't stay in memory for large structures. So I cannot tell you how this will perform without direct fine tuning. But for other models, like for example, this model over here, the ammonia, we did conservative training, which is basically, of course, it's not fine tuning, but you can grasp that you still obtain good performances even if you do conservative training. Yeah, so I cannot tell you more about fine tuning because we didn't do it in this test case.
Sure, I see. That was very interesting, though. So I would ask everybody if there is any other question. If not, we can thank Dario again.